some machines for like micro 3D printing and that kind of a thing. We'll just because it has also a lot of mechatronics to it, so I thought it may be better to kind of participants to they may like this kind of a deliberation that mechatronics. How do you use this mechatronics to really create these micro scale components? And what are the important aspects to worry about there? Okay, so. This we have already seen now. We'll not get into these details. This time scale also we have looked at. Yeah, so see, for example, here the spacing of CD-ROM drive tracks in the practical, in a manufacturer or what do you say, non-natural kind of a world, huh? We have a CDs. You all have seen CD drives and DVD drives and hard disk drives. So the tracks spacing is less than a micron nowadays. Okay, so you have this blue ray optics coming. In that it is less than 1 micron. Normally it is 1.6 microns kind of a spacing of the tracks. And you can imagine for such a kind of a small scale spacing, you have a technology in place to read the data from the surface of a CD and hard disk drive. Okay, so that is a very fine mechatronics in business there. Okay, so those systems now are available at throwaway price, like 2-3 thousand rupees. You get one CD-ROM drive, or you can use your old CD-ROM drive from old machines and hard disk drives from a lot of these repair shops will have these things available, and one can open up them and start using them for a teaching purposes. That's the idea is what we usually do at IIT Bombay. That my first lecture of the course begins with first or second lecture begins with this opening of the CD-ROM drive. So we give actually these kind of devices to students, and then they open up and get hands-on learning done there. So what are the different systems there, and what is the purpose of that? So that is very interesting kind of aspects to bring out from the mechatronics perspective. Okay. So this is an important kind of teaching aid that can help in a low cost or hardly any cost there. And then there are a lot of fundamentals that would be discussed in terms of design of mechatronic systems from such kind of a opening of some systems like that. Okay, and then we'll talk about now. So those in fact those systems can also be used for some of the elements from those systems can be used to create your own kind of a mechatronic system as well. Okay, and you can really touch upon very these fine aspects of micro nanoscale motion by taking components from these systems. Okay. So maybe we'll have chance to talk about some other time. Okay, so now we know these are see this Pentium chip. If you look under microscope, it's going to look something like this. Okay, a lot of these are all like transistor devices. So this is Pentium 4 die. Okay, this is 180 nanometer kind of spacing and 42 million transistors on board. Okay. Now, how do they fabricate all these things? We'll see some of these technologies, which are VLSI fabrication technologies, which can be used for the MEMS fabrication in some way. Okay, so for the fabrication, we need to know about what is this material for MEMS. Okay, typically silicon is a chip material that is used, or this is a material used for fabricating electronic chips or these transistors because it's a semiconductor and it can be doped to kind of give you different levels of conductivity. And from mechanical perspective, this is stronger than steel. Okay, and it is very light as aluminum. Okay, and it can be coated with variety of different kinds of materials. Okay, so this is available typically in the form of these wafers, 2-inch, 4-inch, 8-inch kind of a diameter wafers will be available for these. And then these wafers can be used for processing. Now, how they can be processed, I'll show you how different processes are done to kind of out of wafer, on the surface of wafer you get some kind of a mechanical moving components and things like that. And there are many other materials that are possible which can be deposited on the surface of silicon, and I think I have some list of some of the materials there. Okay, so these are only like partial list. I mean, there is a huge number of materials people have been uh, investigating and using for, including like piezoelectrics or piezoelectric materials and things like that. But these are the typically traditional materials that are used in the chip fabrication technology. And typically like gold, aluminum, copper, those are the metal materials are used for like making contacts. Okay, or like you have some kind of a contact lines which are made up of those materials. So now the question is, how do you kind of fabricate these very tiny chips or tiny kind of a MEMS devices on these silicon wafer? And the main fabrication philosophy is very different from the philosophy that mechanical engineers typically are used to. Like what we do is we take a big size material, we machine it down to small sizes and process it to different kinds of lathe process or milling process or to get a proper shape. But there, what we do is like we typically define those where to cut and how to cut and all those kind of things are those areas are based on say either CNC kind of a process or like manual kind of a process. We know okay, well, this much this diameter is to be reduced to this diameter, like that. You have some kind of drawings according to which you do this machining by inspection. Uh, so in this scale of wafer fabrication processes, the areas where the material to be removed or material to be added is defined by some process called lithography. Okay, or it is also called patterning. Okay, so what is this lithography process? We'll see that in details later. But basically, you create some kind of a mask and define the places where you want to add material or you want to remove the material from. Okay, those places you define by using this lithography process, and once those that is defined, then you carry out this chemical way of removing material. Okay, chemical etching process or plasma etching process are material removal processes, and then you have some material deposition processes. So whole MEMS fabrication can be summarized into all mainly these three activities. One is patterning, then other is material removal, or other is material deposition. Okay, so this combination of these three things will give you many different devices. Okay, so this is a base philosophy that you should be very strongly understanding. Strong understanding should be there to really understand how the MEMS processes. Our normal thinking in mechanical domain of like doing the machining and creating some component out of it, that kind of a philosophy doesn't work here. Okay, because all these material removal processes are predominantly surface processes. Okay, and this material deposition also is a surface process. It's not a volume process. Or in third dimension, you cannot add material. Okay, in these MEMS fabrication processes typically. Okay, you can have multiple layers deposited, but you cannot have a deposition of a volume in one go. Okay, so that is a very different way of thinking that one has to develop slowly to really plan your fabrication. Yeah. Okay, so let us see now this process a little bit more in details. Okay, so how this lithography is done. Now what I'm going to show you is in some kind of a animated fashion. Okay, but it is not to the scale. So you don't think it in terms of the scale whatever is drawn here. No, that will be completely wrong notion that you will carry otherwise. It's just a way of depiction so that you can understand. Otherwise you cannot have like something of the wafer size, and then the layer thickness is some few nanometer kind of a layer will be there on the surface of this photoresist. You cannot draw that for a understanding purpose. Okay, So what we have drawn here is at a bigger kind of a sizes and scale. It is not scaled version definitely. So scale for the material deposition and as against the wafer that is drawn, it is very different. Okay, so this lithography process starts with your wafer substrate. Then you have you put a drop of a photoresist here. Okay, this is photoresist is something like what do you say, a chemical which is the name suggests photo. It means it is light sensitive. So you have these light sensitive chemicals. When they're exposed to light, they'll have some kind of a chemical change that is happening. So we'll see what is what is that change for the positive photoresist, for example. So you take a drop of that photoresist on the surface and then you start spinning this wafer at a very high speed. So there is a spin coating machine that is available. So all these now processes will use very high-ended machines, okay? And these machines are available standard in the market, costing crores kind of rupees actually. So they are not very low cost kind of machines, okay? So so you put this wafer on the spin coater and spin it at very high speed, or and put a drop of this on the top and spin it at very high speed, and then you will get this coating of the positive photoresist on the surface of a wafer. So you spin it at very high speeds, then extra photoresist will be thrown off by centrifugal forces, and whatever the coating that you get will be very thin. So higher the speed of spinning, lower is the thickness of the photoresist that you will obtain on the surface. Okay, and then you expose it at certain points by using a mask. Okay, there is another concept that you use this kind of a mask where there is a window. Now this window need not be like a physical kind of a hole. It's just that some part of the glass is coated with metal to create this mask. So other part is transparent to the light. Okay, so from this part the light can pass through, but from other part the light cannot pass through. Okay, so typical masks are fabricated out of a glass substrate and a chromium coating on the surface of that. Now, how the masks are themselves fabricated, we'll see that later. Okay, there are different processes to do that. Okay, so this mask is put on the front of a photoresist. Now this distance typically between the mask and this photoresist is hardly like few microns, like 10 50 50 microns, 25 50 microns. So it's done in a very very controlled kind of a displacement device. Okay, it's called mask aligner. Okay, so this mass aligner or exposure kind of a machine, okay, or lithography machine. In that, this you insert these wafers into that, and then the mask you also put into that machine, and that machine will take care of getting this mask and wafer close to each other within 50 microns or that kind of a number, so that the light, when you expose, the light has no chance to spread in other places where it is not required. So you expose now this to the UV rays, and something will happen to this photoresist. Okay, but for this positive photoresist and negative photoresist, whatever you are using, something will happen there. Now we'll see in a minute why it is called positive photoresist. So when you develop now, then with a positive photoresist, this affected area will go away. It will get dissolved in the chemical called developer. So every photoresist will come along with its developer. Okay, whenever you expose to the surface, a typical process will be you deposit a photoresist on the surface of paper, then expose to the light, and you pass the wafer to the developer. So this developer, so you'll have now this wafer coming out of your lithography machine, that it is already exposed to UV light in the lithography machine, and then you put it in a developer, okay, or you insert it into a developer bath, and a part which is where the UV light has fallen, that part will get etched away, or that part will get so that's what process called development will happen, and rest of the part will become little harder. Okay, So this is how like typical photoresist the lithography process will happen. Okay, this is one step in entire kind of like many steps the wafer will undergo for getting the final devices done. Okay, so this is how what the positive photoresist can be used to create some kind of a places where now we have opened this kind of a window through which I can pass my chemical and some part of the wafer can get etched, or I can use this window to deposit some other material in these, so that that material will get deposited only in this place, and at other place when I kind of remove this photoresist, that material which is deposited on the top of photoresist also will get go away. So we don't have a way of machining only at one particular point in the system, the way we have when the tool goes there in the case of our normal big size machine. Okay, if you have a shaping machine, that wherever the shaping tool goes, only that place the material will be removed. But now, for that kind of facility is not there in this typical wafer processing processes. That's why you need the lithography step to mask the area where you don't want the deposit to happen, or you don't want that area to get etched. That area you actually prevent, or you can mask that area in some way, so that this whenever I now take it for further processing, this area under this brown kind of a window will not get affected at all, but here some deposits will happen and things like that. Okay, so this is a basic philosophy of processing and thinking in the MEMS domain. Okay, for negative photoresist, the exactly opposite phenomena is going to happen. You start off with the wafer, you coat this surface with the spinning process, and you expose. Now with the exposure, now this part which is getting exposed, that will remain after processing, and the other part will be gone. Okay, so this is called negative photoresist. So there are these both negative and positive photoresist that will be there in the on the surface. Okay, where whatever you want to use, you can use for your own processes. Okay, you have a choice to use. Okay, and when you pass to developer, this again will become like a stronger material. So there is a material called SU8. It is like a negative photoresist material, and that can be that material itself can be used for any lot of fabrication processes, polymer material fabrication process in MEMS. Okay, so these are the main kind of lithography is a main step for defining the areas where you want to put machining or you want to remove the material from. Okay, so you can see some of the pictures of this equipment here. Now this is a spin coater actually. So you have this cover for the top, and then this is small little kind of a thing that you see. There is a stage on this black color O-ring that you are seeing there. So you put a wafer on the top of this surface and you create little vacuum there. So this O-ring and the wafer, like that area between that, you create a vacuum, so the wafer gets kind of held by vacuum to the substrate. So there is no other way to hold the wafer otherwise in these typically in the MEMS processes. So you can see some of the wafers they are undergoing a step called pre-baking. Okay, so these steps are kind of so what I'm showing you is like just some kind of a conceptual view of what is happening, but actual processes are way too detailed processes. For example, these wafers are going to undergo something called RCA cleaning before you before you pass it to. Let me see. There's some kind of questions coming up in the chat box. I can see something popping out. Let me keep the chat here. Okay, so yeah. Uh, okay, so let's So see, I'll just kind of take some questions first and then maybe come back to this. So application of MEMS, maybe we had in the last class, but then last lecture time was up, so but maybe we'll talk later. Let's see how much time we'll have. Flaring effect means like you are talking about some kind of a what you say, this flaring effect is happening because of like diffraction in the lithography. So there are different techniques of reducing that kind of a effect actually. Okay, so this diffraction. So when you expose through light through a small window, then the light will flare up when as the window size starts decreasing, and that is that effect. To reduce its effect on the wafer, you need to, that's why we need to kind of get the wafer very close to the surface of the photoresist. I mean the close to the surface of the mask, so that the wafer and mask, when they are very close, you don't have much room for that flaring to happen. Okay, na? The deposition is performed on the substrate. Wafer itself is a substrate actually. Typically wafers are called substrates. Okay, so these wafers are used as a substrates for, like, starting these MEMS processes actually. So you may use this wafer itself as a participant in the MEMS kind of a material, or you deposit some materials on the top of this wafer and then use them for machining. But wafer is now just acting as a substrate material. It is not really participating in any MEMS kind of a device material. Okay, it's a substrate is like a support. Okay, all right. So what I was talking about is like for even for some simple process like lithography, the lot of other steps are followed before. Like the wafer is cleaned by some process called RCA cleaning. Then you do this kind of a small deposition or spin coating of this what you call this photoresist. You coat the spin coat, and then after spin coating, it is given a pre-bake. Okay, before it is going to this lithography machine, it is given as this kind of a pre-bake on in the oven for some time, or in oven or on a hot plate for some time. Okay, and then once that pre-bake is done, then you take it to the machine, and then you process it in the machine, and then again after processing, you bring it back to this hot plate and do something called post-bake, or you develop and do the post-bake. So there are different kind of protocols that are available, that one has to go through all those kind of processes to then finally come to the point that, okay, oh, you have just done one kind of a process of lithography, one exposure of lithography. Okay, then this is a spin coater. You can see here, this is a O-ring here on which, like, you place the wafer and then you switch on the vacuum, and then the wafer will be held firmly there. Now, there is other kind of a lithography. So the natural question comes, okay, how is mask done? Okay, so this mask is prepared by using this kind of a lithography called E-beam lithography. Okay, so this, what is done here is, as say is clear from here, is electron beam is used to draw something on the surface. So you use a similar kind of a photoresist here, but then now you start like scanning the surface with the in the vacuum. Okay, with a very fine size. So this electron beam can write down to the dimension of about 20 nanometers. If it is tuned properly, you can really get the features of 20 nanometers very easily with electron beam. Typically 50 to 100 nanometers features that you get. So you scan one line of electron beam, you'll get beam line thickness of, or whatever is photopolymerized in that will be of a dimension of about 50 or 100 nanometer. So this, when you want to get into the nanometric kind of a sizes, then this electron beam lithography is very useful, and it is also used for preparing of the preparation of the mask. Okay, and this itself, the electron beam lithography will not need any mask. Okay, so this is one this is like a process which is maskless, but it can be used for preparation of the mask, because you are scanning the electron beam on the surface of this photoresist. And also there is, instead of like, you can say, okay, oh, why electron beam? I can use light also, like our laser light also. Yes, that is also can be possible. One can use our optical light scan, and then that becomes a like a direct laser writing process. Okay, that will have a feature or resolution which is much different from electron beam. So electron beam can go in submicron sizes up to 50 nanometer or so, and a typical laser writer can go maybe up to a micron or 2 micron kind of feature sizes. Okay, so this is how, like, you do that. And if you are not interested in that kind of a very small sizes, then one can use even the printed mask from the printer. Okay, so typically for bigger size dimension, like 100 micron, 200 micron kind of a sizes, in our lab also here, I mean, people use very fine, like, very high DPI printed transparencies. Okay, that plastic kind of a sheets which are printed with these features. They are used as a masks in the mask aligner machines. Okay, so you can have this varied kind of a based on the dimension, you can have different possibilities for mask to be prepared. Okay, mask to be used actually. So very fine masks, like, they're very costly actually. To get the mask themselves is very costly affair to do. So in general, these processes are costly to even consumables, and in the what you say, capital investment or machine itself is very costly. So so that's why, like, this setting up a MEMS fab is not a trivial job actually. It needs a huge amount of funding, and over the years in IIT Bombay we have developed, like, our own MEMS fab, and also there is a nano electronics kind of a fabrication facility now. And this facility is available for users across India to use it under a program called INUP. So you search for this INUP and you will find, like, that under that program you can write your proposal, what you want to process, and all the costs will be taken care of if your proposal gets accepted. Okay, so this very nice way, like, the government has funded this India Nanotechnology program. Okay, and that is now available, like, I think across 4 or 5 centers across the country. ISC, IIT Madras, and IIT Delhi, and a couple of places, other places this program is available. There you have a good idea, you have a fairly reasonable idea. It's not need like, no rocket science is required there actually. You have a reasonable idea, and then you want to fabricate such devices. You propose your process of fabrication, and then your proposal gets accepted here, and then all the costs of your travel coming here and processing your processes, and then getting that training done, and then you take your devices and go back, that everything is covered under this program. Okay, so do make use of this facility. Of course, in the COVID situation, we haven't had the opportunity for this program to be happening, but the labs are working. So now as the things are opening, you can kind of come and do this. Okay, so there are a lot of these machines available. You can look at this INUP program, and INUP, not OP, India Nanotechnology Users Program. Okay, Deepak. Yeah, thanks. And you'll go to INUP website, and you'll have, like, these all the details available there. You can look at and avail this facility. Okay. Then under that we have a lot of machines. You'll get a list of machines that are available under this program, and there'll be, you name it, and those machines will be available. Like, a lot of these deposition facility, or etching of different kind of materials, and then mask aligner, double-sided mask aligners. All those kind of things will be available here. Okay, now let's move on to kind of get into little more fundamental processes details, and then how to make use of this create some devices is what we'll look at. Okay, so now next process following the lithography will be either etching or either material removal or material deposition process. So this chemical etching is the simplest kind of etching process where this mixture of hydrofluoric acid HF nitric acid is done here to act as an etchant, and you put this wafer with this small little window open here into this etchant, okay, and it will start etching the silicon wafer surface, okay, and it will create this kind of a cavity. So if you want to create some kind of a micro challenge in silicon wafer, this is a way to create that, okay. And then there are different rates of dissolution with agitation, without agitation, something will happen different. So without agitation for 5 minutes, it will just happen like that. Then if you do it with agitation, then like you'll create really big cavity here. And if you see, there is typically this kind of a feature called undercut will happen. Okay, so you'll have this the cutting happening below the mask. Okay, so depending upon how much time of exposure you have, you know how much is undercut going to happen, you can create a mask which will compensate for this undercut. Okay, that is a kind of a possibility that exists actually. So those are kind of a more kind of a gory details of the process and process optimization to get these kind of a features transferred in a desired kind of a way. Okay, and people have to do that, this process optimization for every single step in the processing of wafer. One has to do this process optimization to make sure that things are done in a desired kind of a way. Now, anisotropic etching is where this crystallized nature of the silicon single crystal wafer comes in picture. So silicon wafer is actually a single crystal wafer, okay, and it's all the atoms inside it are arranged in one particular fashion in that wafer. So there is say if you select 110 kind of a wafer, okay, then all the atoms are arranged in that wafer such that this 110 direction is perpendicular to the plane of the wafer. Okay, and there is some kind of a directional dependency for some of the etchants. So this KOH, EDP, these are kind of typical etchants that are used for anisotropic etching, and some of the directions. So your wafer has some kind of a direction so that the atoms are oriented. So when you ask for a wafer, people will ask, okay, what wafer you want? 110 wafer you want or 111 wafer you want? Depend upon that, what you select, if you select 100 wafer, then the 100 direction of the crystal of silicon is aligned to the top surface of perpendicular to the top surface of the silicon wafer. That is a kind of a notion that people use. And typical wafer will have a small little cut on the side which will indicate 110 kind of a direction. Okay, so those directions, this is 110 kind of a direction it will be indicating. Okay, so those directions are important for anisotropic etching. Okay, so depending upon so this, suppose I take 100 wafer and I open some windows, then what will happen is since this direction has a lower etching rate, I'll get surfaces which are not etching at that kind of a speed where this orientation of this direction is there. So see 111 direction is this here on the surface. So I get some kind of a cut which is at this angle to 110 direction. Okay, that's what is going to happen, because in this direction etching is not going to proceed that fast as it proceeds in other directions. Okay, and that's why this kind of a cavities will be created. Okay, and these are very very defined angle that will be produced here based on the silicon geometry, crystal geometry. Okay, so this is very useful for creating some kind of a slanting kind of a shapes in whatever MEMS geometry that you need for any application. So you can produce these slanted grooves. Or if you want exact vertical wall, then you need to select a wafer which is different direction such that 111 direction is now vertical. Like that, we can kind of plan some things like that. Okay. So say for a 110 surface wafer is where like you'll have some vertical lines and then some slants are produced. So this there is a lot of crystalline geometry that one has to kind of look into to really understand which direction wafer I should use and and on the surface which direction will have these vertical grooves or not, thing like that. Okay. So that one has to go into more details when you want to use it for your own application. Other type of etching is called plasma etching. See, typically plasma is used where you have very low temperature kind of machining, or you don't want to subject your wafer to very high temperatures. Okay, then you go for plasma etching, and also plasma etching also is a directional etching. Okay, so see, unlike this isotropic etching which progresses is all directions. So if you sit at this point, then the etching has happened here also, etching has happened in this direction also, and all the directions possible etching has happened from this point. Okay, so that is isotropic etching. But if you want exactly vertical kind of a surface to etching to happen, and you don't want it to be dependent upon these wafer directions also, then this plasma is a way to go. So what is the plasma? Plasma is a gas which is exposed to these electric and magnetic fields which are switching at very high frequency. Okay, so this voltage is switching at very high frequency. Okay, and the because of this high frequency, um, the electrons and ions in this gas, they start moving at that kind of a speed from one place to one electrode to other electrode. Okay, and during that motion they start ionizing more gas, and some kind of a stable plasma is produced in the process. Okay, and since these are directed in one particular motion, this motion, since it's a AC field, this is an oscillatory motion that will happen in this direction, and these ions which are typically big mass, so these ions which are typically big mass, they'll kind of hit the wafer surface, and when they hit the wafer surface, physically they remove the atoms from the surface. So these are like dry processes. Okay, you don't have chemicals here to like which are typically liquid chemicals that are used in etching process. Okay, hydrofluoric acid or like nitric acid and things like that. Okay, so acetic acid and things like that. So those are not used here. Here there are these ions which are high mass ions which are bombarding the wafer surface, and they are physically trying to remove the molecules of the silicon from the surface by that heating. Okay, and that's why this is called a dry etching or plasma etching, so to say. Okay, and it is only in vertical direction or particular direction because the voltage is applied between these two electrodes. Okay, so the motion is along the vertical direction for ions and electrons, which is in oscillatory fashion because it's a AC voltage applied here. Okay, so these are machines that are available for such a process, etching process, and then you do this etching. Now you can introduce some gaseous species which are chemically reacting to the wafer surface. Okay, then it becomes like a reactive ion etching. Okay, so now the ions are not only bombarding the surface, but they are also reacting to some and producing some reaction products during the process. And plasma is since they are in ionic form, their reactivity is enhanced. Okay, so this that's why this reactive ion etching is also a very popular process in the MEMS, because it produces very straight walls and very controlled process, and you can go quite deep by using something called deep reactive ion etching. Okay, where you want like straight vertical and very deep kind of a walls, that time what you do is like you use this plasma etching and deposition in 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 what you say in some kind of a sequence. So you first kind of etch some part, then you introduce a gas in the same chamber, which will have some kind of a deposits that will happen on the surface of a wafer. Okay, then you switch again the gas, which is reacting to the wafer surface, and you start like this plasma etching. What will happen is the side walls will get protected because of the deposition of the previous material. When the side walls get protected, you have a chance now to go deeper. Otherwise, in reactive ion etching also there is some chance of, instead of exactly vertical walls, there is a very slight slant can be produced in the walls. So that will be prevented if you do this deep reactive ion process sequence. Okay, and that is used a lot in the MEMS, because you don't want the materials to be subjected to very high temperature, which may typically happen in normal etching processes. Okay, and for deposition also now the plasma can be used. Okay, that is called sputtering process. Okay, now these are, now we come to some deposition processes. So now I'm giving only some few examples of the very common and standard processes that are used for deposition or etching. Okay, it's like long list of processes. We cannot go through that in this kind of a short talk of about 1.5 hours. But one has to go through this entire course of MEMS to really get to the all the details and be able to kind of do these processes by themselves. Like yourself, you want to do these processes. Oxidation is one of the very interesting deposition process, because what you need to do is just need to keep the wafer in the furnace at a high temperature. Okay, there are these kind of a round quartz furnaces that are available. In that you put all your wafers in some kind of a small wafer holder, and then insert them into this furnace, which will heat them at temperature of 1000 to 1200 degrees. And when you take some silicon to that high temperature, in the presence of atmospheric air, like you start like the oxidation process. Okay, and then oxide starts growing on the surface. So some part of the silicon on the surface is consumed and transformed into silicon dioxide. And then the thickness of that dioxide is very well characterized by these equations and processes, and that A and B constants can be determined. All those things are in place. But in the process, you deposit like very thin layer of the oxide on the surface. Okay, it's very well understood control process. It is used for a lot of these processes in the fabrication of chip also. So typically the gate material is used as oxide. Sometimes the oxide is used as a gate material in the transistor. Okay, so things like that. Some small layer of insulation you want. You very thin layer of insulation you can get by this oxidation process. So really nanometric size layers you can produce very nicely controlled manner. Okay, so these processes, Suresh has asked about processes with 5 nanometer, 8 nanometer. So this is these are the processes that will, the dimension of that kind of a size you get by using these electron beam lithography kind of a processes. And then the thickness usually is in the dimension of 5 or 10 nanometer kind of a size. Okay, the even the what you say, the other dimension, the spatial dimension can go down to that value uh, by so electron beam can go to 20 nanometer kind of a dimension, but below that you need to go for ion machining or ion etching processes. Okay, and thicknesses of 5, 8 nanometer are very easy to obtain. If you want the thickness dimension to that, it is by this oxidation and other processes, it is very easy to obtain the control parameters in that process, and then you get those kind of thicknesses. Okay. Same sizes you can get whatever number of devices you want to get. Yeah. So you open the like no, see wherever you do this oxidation, where you do this, window opening or lithography, this size, if you do now this for multiple processes or multiple kind of a places, okay, this window I have shown only one window here. You open how many, whatever number of devices you want, like that many kind of features on the top of the wafer, and that many devices will be coming in the same kind of a processing with the same size it will come. Okay. Yeah. Then let's talk about some kind of a combination of these processes. Before that, we'll look at this sputter. So this is a chamber in which like sputtering can happen. Okay, so the vacuum is created, and then you create a plasma, and then the plasma will now, instead of like wafer that is at a target, you have a other material which is on the target. Okay, this target material is where the ions are bombarding with a very high speed, and this target material will now get, the molecules of the target material will get dislodged from the surface of the target, and then they'll get start depositing everywhere, not only on the surface of wafer, but in the chamber everywhere. So chamber walls also will get deposited with this target material. Okay. So typically, that is what happens when these molecules are getting dislodged. Some part of the, like, certainly will go on a wafer, but some molecules will also kind of get deposited on the walls. That's why these compatibility issues are there in MEMS processing or in this electronics processing. That okay, if I'm like using one material for sputtering, I should not be using other material because the contamination will happen in that chamber. Because previously deposited material, okay, that some traces are that traces of that will get mixed with new material, and I may not get purity that is required for whatever purpose that I'm using this material. Okay, the typical deposition rates are very, very slow. It's 1 micron per minute for aluminum, for example. Okay, and this is done at very this process happens at very low temperature. So then these issues like thermal expansion. Okay, so if you deposit something at a high temperature and then cool it down, then relative thermal expansion of the wafer material versus the material that is getting deposited will create stress. Okay, so alpha, the coefficient of thermal expansion, if it is not same for both the materials, they'll cool down with the same temperature, they'll expand differentially or they'll contract differentially, and that differential contraction is going to create stresses in both the materials. Okay, so these residual stresses are one of the very important aspect that one has to keep in mind while processing your wafers, to make sure that you get a films which are not cracked or which are not kind of subjected to these high stresses. So you may need to follow some annealing process or something like that to relieve the stresses. Then now we put this combination of these processes together to say for if you want to create a cantilever on the surface of a wafer in some material. Okay, so this is a process that is used for now. So we are now using combination of these processes to really create something which is of interest to us now. Okay, so far we have seen these three fundamental processes, and now we'll use the combination of these processes to create something interesting. So first you take a wafer, and then you open some small window and deposit something on the top of that. Okay, so you expose now. So now this deposition, this green color deposition is say material on of which you want a cantilever to be there, and this brown color is your photoresist, and say let's call this like say this material is say something like aluminum. Okay, so you want aluminum cantilever to be standing on the surface of a wafer. Okay, so this is aluminum material I'm using, or you can have many different kind of possibilities here. Okay, or silicon oxide, you can deposit oxide also. Okay, so deposited films also can be possible, rather than like growing oxide, you can deposit oxide by using some kind of a sputter process. And then this yellow color is a photoresist that is now spin on the surface to kind of create dimensions of your cantilever, and you expose that. Okay, Then you start etching away you develop the photoresist and etch away the remaining part of this material that is deposited. Okay, and then you remove this or ash. This asher is a process. You burn out this polymer here, and what remains on the surface is your standing cantilever. Okay, that is a very simple way you can kind of create one cantilever with two mask kind of a process. Okay, so see, any process will be characterized in terms of number of masks that are needed to create that process. Okay. So this is one kind of a see, we have not used now surface silicon wafer in this process at all. That's why it is called surface micro machining kind of a process. Okay. So in 3 dimension it happens something of this sort. Okay, so you can see this is an oxide, then there is a polysilicon material that is deposited on the surface to create this cantilever material here, and then you so when you deposit, it will get deposited everywhere, but then you need to use a mask and remove it from the places you don't want it to be there. And then so we have used here, like this mask to protect this material, so that when I put it in etchant, only the part which is not protected will get all removed away, and then this protected part will remain, and then I remove this thing to kind of free my cantilever. So the photoresist is removed in the end to free the cantilever. Okay, so these are like multiple levels. So we have seen only one level of their surface micro machining. So they can kind of put like similar kind of a 2 level, 3 level, like multiple levels of this process, and then you get more and more complex devices done. The Sandia National Lab, that they have done this kind of a process development and characterize these processes and fabricated a lot of different kind of components we use, including these gears and some linkages which are moving and things like that. Okay, so then there are these electroplating kind of a processes where, so this is again a material addition process by a different way of electroplating. So you use some kind of a addition layer, copper layer, then chromium layer, and then actually you deposit this uh, you know deposit this polymer. Okay, this polymer where you open some windows for electro deposition to happen or electroplating to happen. So you open these windows and then you use the electroplating. So this black material is like what is electroplated in the machine of electroplating, and then you remove this material, and then you have very nicely standing features of electroplated material available there now. Then this is a lithography and electroplating combined process with a molding, okay, to get high aspect ratio called Liga process. Okay, so you can get very high aspect ratio kind of a components, okay, by this Liga process. Okay, so you use this now as a mold and then create molded kind of components. Okay. So this Lika process is very nicely getting carried out at RRCAT Indore. One of our students is there. He is working in this domain to create very high aspect ratio comb drives and this kind of motor structures. So now we'll look at some of the non-conventional kind of fabrication processes, which is one of them is this microstereography. Okay, so we know this dynamic mask, or this dynamic mask or DLP printers create this kind of a the patterns which are dynamic patterns in the nature. We can project those patterns on the surface of a photoresist and layer by layer, and then you can form you can, that's how the DLP printer works. Now it's the same thing is done at micro scale. You'll get a microstereography process done. Okay, so this typically these dynamic masks are used, and then you need to use some kind of optics to reduce their sizes. Okay, so the image that is focused on the surface of photoresist is going to be very scaled down kind of an image, so that you get a very micro scale features which are available there. So you can get these kind of a pictures in multiple layers exposed, and then you get actually on the surface these three kind of a conical nature part that is coming up here. Okay, and this kind of a layer by layer process. Then there are other processes by which we can carry out these. It's called scanning process. Okay, this is what you do is like you take a laser and a mirror and scan the laser beam, focus laser beam on the surface of a photoresist, and this vector scan once will produce one kind of a one kind of a layer, and then so see you insert this substrate into the thing to get a layer thickness out here, and then you scan like a vector scan or raster scan or whatever scan you want to do, and then that layer will be solidified. Okay, when you scan the laser, you photopolymerize the photopolymer, and then you insert this substrate again into the system, and then you get the second layer up on the surface of this first layer, and then you scan the second layer, and like that you layer by layer you start building the component. Okay, so there are many different ways of like people have proposed, and we have proposed something new, and in the literature way back in 2006, and we have done some research into this aspect of microcirculography, and we built our own kind of a microcirculography system that is now in its fourth generation. Like fourth generation machine is coming up with higher speeds now in our lab, with very lot of novel ideas have gone into, and we have some granted patents on this aspect and things like that. So the same process, we start with the CAD model. We have some kind of a slicing algorithm to generate scan path, and then we photopolymerize the resin along this scan path, and then we generate this component. Okay, and for this is a system that is what is we have set up in our lab. And for this, we are using these compliant mechanisms for scanning purposes, so that we can position the system within like 100 or 50 to 100 nanometer kind of accuracy. So since we are fabricating micro scale components, we need that kind of a positioning accuracy for the laser beam to position on the surface and get the components printed with a very high resolution. So that is how this microcircularity system is working, and this compliant mechanisms is another kind of a research area in our lab where we are looking at dynamics and statics of these different kinds of these compliant mechanisms in place, and using them for like this kind of a developing the stages which can move in the nanometric kind of accuracy. Okay, so we have done a lot of this kind of characterization, and couple of patents also have been filed on the component mechanisms domain. And there is one company that our students have recently started on based on our research here called Flex Motion Technologies. Okay, so you can look at, if you are interested in yourself to kind of get some kind of a compliant mechanism based nanometric motion stages for any of your applications, then like you can contact them. The company name is Flex Motion Technologies. Okay. Then these are the microstructures. I'm just giving you some idea of. These are like fabricated long back actually. Now we have much better kind of a finer resolution structures coming up now. So these are many different kind of, this is a scaffold kind of a structure that was fabricated. And typically you see that all these processes will produce this stepping effect in the Z direction. As you start having these surfaces which are slanted, on the slanted surfaces you get these steps here. Okay, you can see the steps coming up here. So we develop some processes which will avoid these steps also. Okay, so that is called bulk lithography, is what a name that we have given. This process, what we do here is a very different kind of a philosophy, which is not there in the literature so far. I mean, which was not there in the literature before we published actually. This is again way back in 2011 this was done. So idea here is, this is a photopolymer resin here, and you take a laser beam and focus it at the resin and the substrate interface. Okay, and then some structure starts coming up there. Okay, and then you scan the laser beam, like that structure will turn into a wall. Okay, and as the laser beam is scanning, you change the intensity, then you can shape the wall in whatever desired shape. So the scan path is in this direction, and you increase the intensity, you get a deeper kind of a formation. You decrease the intensity, you come back and, like, you get a smaller fabrication. So you can kind of like tune the intensity to get you whatever is free surface shape that you want. Okay, that is the idea here, and that's what we have used to create some kind of a components which are, say, simple needles like these, or some kind of a very smoothly varying surfaces at a micron scale. So if you see this, this is like 100 micron kind of a dimension. Okay, and on that you get smooth variation from one end to other end. Otherwise this would have been like, just a two layer or 50 micron each, like, or 25 micron each, four layer kind of a four step kind of a material. Instead of that, we are getting now this smooth kind of a variation here. Okay, so so let's not like negate. So there are many this kind of a sensing methods could be embedded now along with these devices. So all the processes that are there available for electronic devices, they can be integrated with this mechanical kind of a processes, and then you can create this kind of a sensing, capacitive sensing, or like, thermocouple effect, or piezoelectric materials you can deposit. That kind of a sensing you can do with the MEMS devices. Okay, so these are some of the examples of this pressure sensor that is fabricated. So you start off with this substrate is now red here, and then the silicon nitride layer, and then epitaxially grown silicon, and insulator layer. Okay, and then you start machining. So this is a entire process is to kind of create a device in this green kind of a material here. Okay, and then there are these piezoresistors that are created, and they are like contacted by these gold kind of contacts. Actually, the gold material is used for the conducting contact material, and that's what will be connected to the outer world to actually get the sensor reading out. This is a pressure sensor that is getting fabricated. So this part will act as a pressure diaphragm, and then this part will act as a doped piezoresistive sensors. Okay, so when they see some stress, their resistance will change, and that change will be registered in through these cold contacts. Okay, so this is a glass bonding to kind of bond this wafer and then create this kind of this is like a third dimensional picture of this piezoresistive uh, pressure sensor. Okay, now this is an accelerometer. So these are some kind of the basic fundamental idea is a similar kind of a processes are repeated like again and again to create these different kind of a cavities and shapes, and like you get this accelerometer in this case for bulk micro machining. So this is a kind of a etching that you carry out in such a way that this cavity gets open, but then there is this kind of a cantilever beam still remains, and is a big mass or accelerometer that is needed to, which is there from the base silicon material itself. I mean the wafer material itself. Okay, so this is not a material which is deposited, but this is base wafer material itself is etched from multiple sides to create a cantilever out of it, and then create a big mass out of it. And now you deposit some kind of a piezoresistive element, and then have a gold contacts to that, and you get this accelerometer working. Okay. So I think this is fine. We'll stop here. We'll not get into much of design considerations, but there are many different devices that can be fabricated in this kind of a fashion. And once you have this fundamental understanding, this will enable you to understand papers in the domain. So you see some kind of a fabrication process given in this kind of a process sequence, you'll be able to kind of make sense of it now. Okay. So there are many different kind of processes people have proposed, and still they are coming up in the literature, and so many devices are there. We have seen some examples of these devices already in the previous lecture. Okay, So we will stop here for now, and then we'll look at some of these are some devices which we have created at IIT, but it's okay. I mean, we'll stop here and we'll look at some of the other technologies. Okay, so we have 20 minutes. So I'll give you some flavor of some research that we are doing in some of the technologies which are different than normal way of doing the MEMS. Okay, so this conceptually really very different ideas have gone into this kind of a way of fabrication. Okay, so I'll share this screen here. Oh, can you see my this new presentation? Yes, no? Maybe I'll stop sharing and share it again. So you can see this. Okay, can you see this presentation?
Yeah, it is okay, sir. But video, sir, it is.
Video is not there.
It is the presentation is visible, sir.
Uh,
But video is
Video,
not playing.
but I don't have any videos. So far, I have
Okay,
not
okay,
played
sir.
any videos
Okay,
so far. So
okay,
it's okay. I think videos are not there.
okay.
There are animations that were coming in the presentation
Yeah, animations
itself.
are coming clearly,
Yeah,
sir. That
yeah.
is all
The
clear on.
video I have not. I don't have.
Okay.
If you this presentation has some videos that I'll present.
Yeah,
That time you
okay.
tell me, huh? Please. Okay, so now what we are talking here is some innovative techniques for microfabrication. Okay, and these are for fabrication of some of these geometries like fractal-like geometries or array type of geometries. Okay, now these are not only for microfabrication, but these are for scalable kind of a microfabrication. So you can have this on a scale as large as maybe a foot long or 1 meter long scale. The same processes will happen. Okay, and I'll show you these are very interesting kind of a processes. So the basic concept I'll tell you, but before that, this is about our lab. So our lab is main theme of our lab is innovation. Okay, so we do a lot of innovative kind of activities, for different purposes in our lab. Okay, and there's a lot of scope for actual collaboration. So if you want to use our facilities, or you want to kind of like say, okay, oh look, this particular process that I like, I mean that we want to use this machine which we have developed for your this process, you want to use it in some way for your own kind of feel free to kind of contact, and we'll talk about. So there are a lot of scope for collaborative kind of activities here. Okay, so this development is inspired by nature. Okay, see, if you see in nature, like the tree, for example, you have multiple branches starting with one big branch and splitting into smaller branches, and then further splitting into smaller branches, like further, it's like a fractal kind of a fractal-like nature. Okay, it's not infinitely long, but it's some finite number of kind of generations together. You take leaf, same thing, but now along with the branches there are some arrays also here, so some kind of a array patterns also you find here. Then in the wings you see this array kind of a patterns, like some kind of a random array, but there is some kind of array patterns, and then some strengthening ribs are there here in between. If you see our lot of systems in biological world, they also have like big size vessels, okay, splitting into small size, and then further really really small size, and that's where the exchange of gases happen there, like your oxygen from the blood exchange in the lungs in this kind of a fashion, and then again, like they come together and then form big size branch. Why they do this like that? Have you pondered over why this is like that? Okay, why not like to have some other kind of a structure? So this fractal geometry is known, is done in this way, and people have studied this, and like they have concluded that okay, when the nature has done this because it needs the least amount of energy to get to do whatever phenomena is happening. In this case, a mass transport. The oxygen mass transport is happening in the lungs, that is very efficient with a very less energy consumption that is needed for the heart to pump blood through to the lungs and things like that. Okay, so this efficiency can be tapped if you are able to kind of replicate these processes at our fabrication ways. How can we fabricate such things where these processes can be replicated? So this is like a wafer processed in a MEMS kind of a processes to kind of get the similar kind of a dimensions with the split geometry heat exchanger, and this has again shown to have very high thermal efficiency of heat transport. And so this in the structural world, these kind of structures, when now we have a 3D printers coming up in the market in big way, you can print these kind of parts very easily. Okay, so you can save a lot of material, and you can get these kind of structures fabricated by 3D printing way, and you can do very efficient job in utilization of material. So these are going to be like coming up in the future in much bigger kind of a way. Right now, our 3D printers are not really used for production purposes as much as for the prototyping kind of a way. Okay. These structures, if you want to fabricate, now what we are doing is like, normally the ways of fabrication, either we know that, okay, this mechanical way of fabrication, or now what we have studied is, the lithography way of fabrication. So both have some pros and cons. And for example, like, whatever is done in resolution, high resolution, will have very small range of dimensions. Whatever is done with a large range, okay, cannot get very small resolution. So this tussle between the resolution and range is always there for many machines. And we are trying to see, like, if we can fabricate some, like, we can have some processes which can kind of get over this tussle, I would say, in some sense. So you can just watch this video. This is inspiration for this thing. Let me get into playing this video. So you can see this video. Okay, maybe yeah. Can someone confirm that, okay, you're seeing this video?
Sir, it is clear, sir.
Yeah, it's clear now. Okay, very good. So you can see that, these some paints are used with a sticky Fevicol material. So like, I'll just fast forward so we can see like how this process is really happening. You use these two different colors to just kind of give some kind of a fancy thing there. Okay, and then so now this is the important process. So you press that color or blue into different glass plates, and now you separate them out and then see what happens. Okay. So this is a motivation for, like, getting this now at the research scale. So this lifting is causing you these kind of variations in the patterns. Okay, you can see this. This is a natural pattern that is produced in some kind of a form. So you just transfer it to the paper is what it is done. Okay, so you can get this pattern now. Like, so this now this how can we use these patterns? Let us stop here, and then so this is why this phenomena happens is explained here. This is a phenomena called Safman-Teller instability that happens here. Okay, and that is very well studied in the literature. It is when you have a low viscosity fluid is pumped into high viscosity fluid in this case, then this doesn't go here as a circle. Okay, it actually splits and goes in as this fingering kind of instability that happens here. The same thing happens when you lift the plates apart. That air acts as a low viscosity fluid, and your Fevicol that was there in the previous case that acts as a high viscosity fluid, and you get this kind of a lifted Helleshaw cell. This is a name that is given to this kind of a process or this kind of a apparatus which is lifted by the Helleshaw cell. And there you get this compressed film, and then you lift apart this film and you get these patterns. Okay, and now the question is, these are random patterns. So we have gotten these patterns in a fluid which is alumina suspension in photopolymer. Okay, so we can actually get many different kind of liquids to have this thing possible. So nanomaterials or like the nanoparticles mixed fluids you can use to get functional kind of patterns here. But the problem is that these are random in nature. Okay, I cannot have the same branches everywhere every time. Okay, every time I do this, something different will happen. So how do you now? And then these are the fluid structure gotten from the fluid. So how you have to retain the fluid structure. Okay, so this is a pattern I want to retain. How do we retain that? And how do I scale this process? How do you obtain repeatable and controlled patterns? Okay, so these are the questions we started off like looking at, and then we came up with some kind of a solutions to that. Okay, so say for example, if you do it with the silicon oil, then these patterns will get formed, but over the time, these patterns will get kind of you can see that they're all coming back to a single drop eventually. Okay, so these patterns will not get retained easily. So for retaining, there is a fluid property called yield that is to be given to the fluid, and then when the yield property is there, then the structures will be retained. Okay, so we have these structures which are retained here. Okay, so you can see that this especially suspension of particles give the yield property. Okay, so these are the alumina suspensions in some photopolymer, and that is giving you yield property, and this is showing that okay, the structures are getting retained, and now once they are getting retained in the fluid form, then we can solidify them by exposing it to the UV light everywhere. Okay, uniform exposure to UV light, all the things will get solidified because it is made out of the mixture of photopolymer and alumina. Okay, so this alumina will be trapped in the matrix of a solidified photopolymer is what your structure finally is going to be. Okay, and then this is scalable. You go at many different scales, you will have the same patterns evolving. Okay, so this is this scalability shown in again over 300 mm kind of a diameter and things. Okay, so this is produced in a scalable kind of a pattern. Now there is some kind of a mechatronics here for like how do you lift this one plate with respect to other plate in a perfectly parallel way or in an angular kind of a way. Okay, so some innovative concepts have been proposed from the compliant mechanisms to do that, and we developed this kind of in-house setups. So see, what I'm saying here is like this is not very great like difficult thing for anybody to do. One can use like these simple kind of linear stages to kind of create this kind of parallel motion possibility. Okay, so there is a universal coupling that is done here in between to kind of make sure the parallelity is maintained from the top to bottom thing. Okay, then you have this video coming up here for how this angular lifting takes place. Okay, so watch this carefully. This is a plate which is getting lifted angularly when you have this compliant mechanism is guiding, and then this is point at which the force is applied. So the force is applied here, and then this plate gets angularly lifted in such a way that the remote center of motion of plate is coinciding the edge of the plate here. So there is some kind of a mechanics going on here. Okay, then how do you get controlled kind of a patterns? So instead of random patterns, you want to get a controlled patterns. You observe this process. You have in here we have seeded some kind of a scratches on the surface. Okay, so there are some kind of a grooves that are made on the surface. And now these grooves act as a preferential points for the air fingers to grow. Okay, as you, so this is so if you observe carefully, the initial step was where the droplet is squeezed and like it starts touching the ends of these grooves here. Okay, so this fluid droplet is squeezed, which is alumina mixture is squeezed, and then it is touching the thing. And now you see here, this where the grooves are not there, you see that the fingers are getting generated in the random fashion here. Okay, you see some fingers coming up here, some fingers coming up here in a random way. We don't know where they'll come. But in the area where these grooves were placed, your fingers are coming only in those places. Okay, and then they are progressing because the groove patterns are different. So if eventually you'll get this kind of a structure where you have one branch splitting into multiple branches into like two branches and two branches like that kind of a pattern. So this is like, now every time you do this process with these grooves, exactly the same thing is going to happen. So that is how you get this kind of a fractal geometry, microchannels, or like microchannel kind of a features on the surface. They are not really microchannels; they are like protruding out of the surface right now. But you can cast PDMS like rubber-like material on the top, and you can create channels out of this now. And we have done that for some bio applications further. Okay, so this is now these processes can be scaled further for different kind of geometries. Okay. So we have studied some kind of a process in the non-dimensional form for the fluid, and then how these kind of fingers are going to progress, and how many kind of generations we'll be able to fabricate for a given fluid that we can predict from this graph. Okay, so this is how we can see the number of generations scaling. Like, this is a fifth generation structure. One split here, second split here, then third split here, fourth split here, and then fifth is in the end like that. 5 times the branch is splitting into 2 branches only, kind of a feature that we have been able to fabricate. And this is very, I mean, very out of the box kind of a process to do this kind of a natural structures fabrication. And these natural structures we can fabricate for getting the efficiency that nature has built into some of these biological systems, and like use them for like some engineering kind of applications. That is a kind of idea. So there is some other variation where we have, instead of now just the scratches on the surface, we are actually putting holes on the surface with the different radial locations for the hole with respect to the droplet that is put on the surface. Okay, and then we get some different kind of structures fabrication here. Okay, so I think we are coming to an end. I'll just show you some video of the entire process together, and then maybe we'll stop at that point. So we have done like a lot of these such kind of a processes for different um, kind of dimensions and sizes and different kind of structures to evolve. This is like a full control with a parallel lifting that is happening here. And this all these setups, by the way, I have built in-house as a mechatronic systems. Okay, so the mechatronic system is just kind of pressing the plates together, and then they're separating apart from each other. And we have used some ball screw slides in some places. In some places, we have used compliant mechanism based guides and things. And you can get this kind of a very high precision, nicely placed symmetric structures here. And so see some kind of a variability, whether if it is acceptable for some application, then this is a good process to go. If your application says that okay, this is not acceptable at all, then no, this process is not for those applications. And you can get this kind of very nice array patterns also. In fact, we have replicated the patterns for the leaf also. Okay, I'll show you that. So this control over different generations is what is displayed here. Then if you see this cross section of these branches, it is changing from like root to the end. Okay, so tips have very small kind of a cross section height, and this has much larger height at the root. Okay, because it's a naturally it is coming up this process like that. So the roots have like no larger dimensions, and that may be useful for some applications. So in particular, we are using this for creating something like a blood-brain barrier on a chip. Okay, so replicating our vessels in the brain actually. So their sizes reduce as you go from like bigger size dimensions to the smaller size dimensions, and because of that, the blood flow sees some different shear that is happening. So the walls of the blood vessels, they see differential shear as the blood flows from one branch to the other branch to the other branch and the junction. You see the differential shear, and that shear induces some kind of a tightness of the junctions of blood-brain barrier. Okay, so that shear has some effect in the biological sense on the transport of the drug molecules to the brain or not. Okay, so those are kind of effects that we are studying on the chip that is fabricated by this kind of a process. So mainly bio applications are where these structures are mainly going. So we have done some simulations and then like observe this process very carefully to see how these patterns evolve and what can be done differently. And then now currently one of the PhD students is looking at evolution of three-dimensional patterns. So here is a leaf replication, venation that we replicated. I think this image is not coming here. Okay, but this image is where we actually fabricated a pattern which was captured in this red box here. But then getting this like array patterns at multiple scales. So this is 8 mm kind of a scale, and on the same scale, this is very small kind of a 100 micron kind of a scale that is patterns are coming up. So you can get the surfaces textured very nicely with this process. Okay, so texturing of the surfaces, large surfaces can be done very nicely by doing this process. Okay. So I'll just give you summary of this process and like maybe we'll stop here. This media is not found. Wait, this media is there somewhere. I'll get you this video and then maybe this is an important video you must see actually. I'm just getting. Hmm.
It is not playing, sir. You have
No, no,
not
no,
started.
no, no. I'm not yet gotten it actually.
Okay,
I'm
okay,
locating
sir.
that video from my video file and then I'll play. Okay, just
Okay.
give me 2 minutes.
No problem, sir.
Okay.
No problem.
Yeah,
Take your time.
yeah, yeah.
Because this is we cannot understand what.
So this is an interesting video. I think all of you should see this video. So let me get that file. Okay, I got this video file. Okay, let me share this video file. Huh? Okay, can you see this video now?
Yes, sir. It is
Yeah,
playing, sir.
yeah,
Clear.
great. Yeah. So you can see the way things are done here. So this is a setup for that angular and parallel lifting setup that I was talking about. Let me get a voice. Okay. So this is so we drill this small little holes here. Okay. So this is a setup again for drilling setup is also put together by our students in house. Actually, there is nothing purchased here. Actually, this is already like we had this propeller motors for the aero modeling that will be that were used for high speed kind of a drilling machine creation. And then you have this droplet which is put on the surface. You can see this droplet on the top here, and it is now. So this is a droplet, fluid droplet on the top, and you are compressing it from the bottom side, and between the two plates, it gets spread like that. Okay, in the top view, it looks like that it is spreading. Okay, and then if you do it with a very high speed, then these holes are not respected. So if you want that holes to kind of come in picture for like controlling the thing, you do it at very, very low speeds, and then this will start happening. And this kind of creates the geometries that we have seen. Okay, these control geometries will get created. So that is how this whole fabrication process goes. Okay, and you can get like many different kinds of formations as we have seen before. And this is like no other setup where we are doing this angular kind of a separation. This is a voice coil and magnet kind of a actuator to do this process. Yeah. So this is showing the randomness of the process. You can see how randomly the fingers are getting generated from multiple points when you don't have any control. Okay. So this is what is normally the process Safman-Teller instability is known for. The fingering patterns which are random in nature and unstable in it's not is that's why it's called instability. But then we have achieved this kind of a control part and get gotten this further control with these different sizes and shapes. And we are using now these kind of square patterns for drug testing, drug discovery kind of a device manufacturing. So this all manufacturing without any kind of a lithography and other kind of a costly devices. Huh? So everything is done with this simple machine where we have this process developed in house, and with it is aided by all the mechatronics kind of research that, or what you say, mechatronics system or mechatronics fundamentals that we have put into these systems. Okay, so thank you very much. I think we'll stop here. If and any other questions, if I have, we'll take up them. So yeah, okay.
So few questions are there, sir, in the text box. Shall I
Yeah.
read, sir?
Yeah. Let me see if I can see them. Yeah.
Ah,
Yeah. So some of them I have already addressed while I was talking. Huh. So reference book. So yeah, textbooks on optomechatronics. Okay. I'll have to find out. We have one textbook I have in my office, but I don't recall its thing. But maybe this information, na, I'll note it down and I'll pass it to Dr.
yeah.
Basu. Okay.
Okay, sir.
So
Okay.
so textbook on optomechatronics. Okay. I have one textbook which is kind of good textbook actually. Then current and potential research area in MEMS. There are, see, I think there are a lot of areas for this, MEMS exploration. So I have taken a route which is non-conventional. I mean, it depends upon what your liking is, and depending upon that. See, if you get hooked on to some kind of a INUP or some kind of a thing where you have this actual fabrication possibilities. So I would suggest do something where you are actually doing hands-on stuff. Then only that has a lot of kind of a value that you create. Otherwise, simulations में रहेंगे ना तो you will not understand what are difficulties are in practice, and then how to get over. And you think when you think how to get over those difficulties, that's where some new ideas kind of start coming in. And nature has a good ways to teach. So I would suggest you people, if you want to do something in this, you either get hooked onto one of these kind of a fabrication fab, or like create some of these kind of a innovative ways of like creating these processes. Okay. Then research areas. Okay. Then there are like RF, there are a lot of research areas. Biomems, if you see, it's just your liking you need to see, and then get going with that. Okay. Then reference book in the area of thermal effects in MEMS and applications of MEMS in RF resonator and all. No? Okay, so I'll give you that text also. Okay, RF. See, RF MEMS. A lot of work is done by Ashwin Seshia in the MEMS resonators area. So you see there'll be a lot of papers and books. Books may be also there by Ashwin Seshia from Cambridge University in UK. Okay. So we had conducted one of his Gyan courses on resonators at IIT Bombay. So look for that. So I'll see some books on resonators from his course, and then give you some references there. But I think he was talking a lot of things based on the papers. Then mechanics of beams and diaphragms structures. This is same as normal beams kind of a mechanics. There's not much of a difference for the MEMS kind of a thing. Air damping in MEMS, Rudra Pratap is expert, RP. I don't know, was he a speaker in this course? I don't know, but he's one of the resource persons for damping. He has a lot of good papers he has published on air damping in MEMS. And so see, this normal references will also give you some things, but one has to see the papers for really getting a good grip over these some of these upcoming, this topic of air damping has recently been researched quite a bit. Electrostatic actuation. Some books will anyway talk about electrostatic actuation in MEMS, but so I'll suggest you some general books in which you find these topics. Okay, so I have some list of books in my MEMS course, so that I'll just pass it on. Yeah.
Okay, sir. Thank you.
Yeah.
If the participants have no other questions, then otherwise you can contact sir through email. Yeah, I have shared the email for you. Once again, the sir will share the email. You can contact the sir, and he can able to clear you the doubts.
Yeah, I'll just put my email in the chat box.
Yeah.
And then okay, you can look at this email, and then I'll share also link for this design of mechatronic systems course, NPTEL course on design of mechatronic systems. Okay, it already has about 1,400 registered participants, so you can make use of this opportunity, because a lot of efforts that we have put in getting this course all the video lectures are there already done, and now assignments are getting done. So this will be like very useful course for a lot of students, in my opinion. So you can you can visit this website and see the preview, and from that preview you may get some more idea about, and then the topics also are listed there. So I would suggest you can pass it on to your students to get this opportunity availed. Okay, so thank you very much.
Okay, sir. Thank you very much, sir, for
Yeah.
your nice and innovative lecture. And you have inspired us the new areas on optomechatronics and this MEMS area. I think the participant has gained enough knowledge and the new exposure on that. Thank you very much, sir, once again.
Yeah. So thank you. I'll then leave a meeting. Huh? Thanks a lot. Okay.
Thank
Bye.
you, sir.
Bye.
Okay, no problem.
Yeah.
So, the participants, already the next speaker is already ready. We will take some 5 minutes break, and we'll come back. And he's also another Lalit sir. Are you there, sir? Lalit sir?
Yeah. I'm there, Dr. Bas.
Just can we take 5 minutes break, sir?
Sure. We can take.
Just participants, please come back 5 minutes break, and we will continue. Sorry for because Lalit sir is working in Bharat Atomic Company. That is back. He is told that we have to work outside work during lunch hours only. So that's why we have to forcibly have to kept your time on this time. And you please cooperate with her, and I think the sir will able to give you a nice lecture on the fault analysis of this particular mechatronic system. So we will come back by 5 minutes. Okay, so by 12:50 we will be start the lecture. Okay. Dear participants, okay. Okay, sir. Lalit sir, are you okay, sir? We can start, sir. Lalit sir. Hello.
Yeah. We can start.
Yeah. Okay. So just before today, I will just introduce you, sir. As the time is not there, just tomorrow I will read your brief biodata, sir. Sorry for yeah.
Yeah. That
So
will be good, I think.
yeah. So, dear participants, now we are having another eminent expert from BARC, Mumbai. So, Sir has been obtained his PhD degree from BHU. Now it is going to be called as Indian Institute of Technology, Banaras University. So now today he is going to be giving the talk on the safety analysis of mechatronic systems. What are the important? That is also one of the important concept now people are going to be using. So now because the time is done, then I will hand over the session to Lalit sir. Sir, now you can continue, sir.
Thank you, Dr. Vasu. And just confirm me whether my slides are moving.
Yeah, yes, sir. It is clear, sir. Crystal clear.
And it is moving.
Yeah,
I'm
it is
changing
moving,
the
sir.
slides.
It is moving, sir. Okay, sir. Clear.
Thank you. So I'll be talking on safety analysis of mechatronic systems. And because this FTP is especially for the mechatronic systems, and we know like some of the mechatronic systems are very safety critical in nature, and they are being used in critical infrastructure of the industries or of the countries. For example, in aerospace, in nuclear energy, in automobiles, in defense, in railways. And these are the important critical infrastructures of the countries which utilizes the safety critical mechatronic systems. And safety critical systems, if I talk about, these are the systems, the failure of which can lead to the catastrophic disasters, or even it can lead to the loss of human life. And hence, because of its safety significance, it is